Welcome. In this video, we finish Unit 6 on quadratic functions. Today is day 3, where we look at building quadratic models. We're in section 4.4 from the book, and this is a short section, only 2 objectives. We'll just look at the first objective, which is basically looking at 3 nice examples. Our 3 examples will be maximizing revenue, maximizing area enclosed by a fence, and a suspension bridge. So these are 3 examples that involve quadratic functions, and we can use quadratic functions to help solve some problems. All right, maximizing revenue. So revenue, R, is the amount of money received from selling something. Revenue is how much you get. Now, if you sell X items, and each item costs P dollars, then the revenue is simply X times P, the number of items that you sell times the price per item. So that's revenue, R equals XP. But there's something else interesting that goes on. The law of demand states that price and number of items sold, P and X, are inversely related. As one increases, the other decreases. And you can imagine, right, if your price is very high, then you won't sell very many items. And if your price is very low, then people will love it and they'll buy a lot of your items. You could imagine, for example, that P and X might be related by this equation. So look at this. X, which is the number of items sold, is 21,000 minus 150P. What this is telling me is that when P is small, like say close to 0, then my X is about 21,000. But as P gets larger, as the price increases, it gets larger and larger and larger, I'm subtracting more and more. And so the number of items sold will go down. So as P increases, my X decreases. So in a real life situation, a company might get an equation like this from experiment. They raise their price a little bit, they see how the demand changes, they lower their price a little bit, and they see how demand changes. So one way or another, you can get an equation that relates X and P. This is called the demand equation. Let's suppose that Best Widgets Incorporated makes widgets. They have determined that the demand equation for their widgets is X equals 21,000 minus 150P. We can answer all kinds of questions like this. In the next few slides, we'll take these questions individually, but I just want to give an overview of what we'll be answering. We can find a model that expresses revenue as a function of price. We can figure out the domain of R. We can figure out what is the price that they should charge to maximize revenue. And if that price is charged, what will the maximum revenue be? How many units will be sold? It's all about maximizing. What price should we charge to maximize our revenue? All right, let's take a look at each of these questions individually. So up on top, just a reminder, our demand equation is X equals 21,000 minus 150P. A, let's find a model that expresses revenue as a function of price. So remember, revenue was X times P. So in a way, revenue is not a function of P, but it's a function of both X and P. But on the other hand, my X was actually 21,000 minus 150P. So simplifying that, I get 21,000P minus 150P squared, and that's really it. So my revenue is now expressed entirely in terms of price. And look at this. This is a quadratic function. Now, in the quadratic function, I have a x squared plus bx plus c. My a is negative 150, and the b is 21,000. So this actually, if I were to graph it, this would be a downward opening parabola. This kind of makes sense for revenue. Let's imagine that if my price is very small, let's say my price is close to 0, well, okay, again, looking at our revenue function, if P is close to 0, this value will be essentially 0. I won't make any money. But as my price increases, then I'll make more money because each item costs more and people will be buying these items. But there comes a point when the price is too high. And if the price is so high, then people won't buy very many items, and the revenue will drop, and eventually the revenue would become zero again. So it's really a great question. What is that price right in the middle that will maximize my revenue? Well, first of all, let's address B. What is the domain of R? In fact, really asking what is this point on the right? What kind of prices should I expect if I want my revenue to be at least be positive? One way we do this is to solve where does the revenue equal zero? And so I'll actually find where it equals zero, where it crosses that axis. Now I can factor a p out of that expression, so I get p times 21,000 minus 150p equals 0. And now that it's factored, I can see, oh, either p equals 0 or 21,000 minus 150p equals 0. And I've already done the calculations. I'll tell you, it turns out that p is 140 for that to be true. So either p equals 0 or p equals 140. 140 over there. C. What price should they charge per widget to maximize revenue? So we're really asking about that number in the middle. Now, a good guess would be 70, because it looks like that number is right in between 0 and 140. But how can we figure that out officially? We think about the vertex of the parabola. That parabola, the x value, or in this case the p value of that vertex, is negative b over 2a. And by plugging in the b and the a into negative b over 2a, I can find that, oh, it is indeed 70. So if I charge $70 per widget, that will maximize my revenue. That's kind of a nice real-life problem. Well, there's a little bit more. Let's suppose that that price is charged. What will the maximum revenue actually be? So if I do charge $70, the horizontal axis is price, the vertical axis is actual revenue, what is the dollar amount that I will get? How do you figure that out? Do you know? We just plug it right into our revenue function. I figure out R of 70. So 21,000 times 70 minus 150 times 70 squared, and we get 735,000. That goes right here, $735,000. That was D. How about E? How many units will be sold at this price? How do I figure that out? And I can remember that I have a demand equation. This tells us the relationship between P and X. So if 70 is the dollar price, then X equals 21,000 minus 150 times 70, and we find that 10,500 items will actually be sold. And there's the graph. One last question we can talk about. How much should Best Widgets Incorporated charge to collect at least $675,000? Here's the idea. We know that the maximum it can attain is $735,000 when it sells its widgets for $70 a piece. All right, so when it charges $70 per widget, it maximizes its revenue at $735,000. But what if it's aiming for a more modest goal, $675,000? So that's somewhere down here, 675,000. Well, in this case, I have two different values, and I'm really after what are those prices. I want a range of values. So what prices should I charge, roughly, to the left and right of 70? That will give me a revenue of at least $675,000, so somewhere up there. How do I do that? How do I figure out those two x values? Or I should say, those two p values. Well, what we do is we solve R of p equals 675,000. And so to do that, I have my R of p, which is 21,000p minus 150p squared, and I set that equal to 675,000. So this is the equation to solve. Now, it might take a couple steps that I'm leaving out here, but I want to turn this equation into standard form. So I want my p squared first, and then the p term, and then the constant, and I'll multiply appropriately so that this is a positive 150 out front. So see if you can do that, see if you can make sense of that I can turn that equation into sort of standard form here. Well, now what? It looks like a standard quadratic equation, but the numbers are pretty big. I guess I would like to maybe divide out by 150. Can I divide both sides by 150? Fortunately, because this problem is cooked up, yes, I still get nice numbers when I do that. And now you start to wonder, does this thing actually factor? Can I find two things that multiply to make 4,500 and add or subtract to make 140? Yeah, with a little bit of guesswork you can. You find that p minus 50 times p minus 90 equals 0, and again, because the problem is cooked. And so, whoops, typo here, this should be 50. P equals 50 or p equals 90. And those are the two numbers on my axis, 50 and 90. So as long as the price is between 50 and 90 per item that I'm selling these widgets for, each widget costs between $50 and $90, then I should be able to make at least $675,000 in revenue. So Best Widgets Incorporated should charge between, say, $50 and $90 in order to collect at least $675,000. Another example. Maximize the area enclosed by a fence. You have 2,000 feet of fencing to enclose a rectangular field. What dimensions of the rectangle maximize the enclosed area? What we're asking for are the dimensions. A rectangle has basically two dimensions. It has width and it has length. Let's call the width W and the length X. And I want the area to be maximized. So what is the area of a rectangle? It's just length times width, right? So if this rectangle has width W and length X, its area is WX. Well, now what? It seems like there ought to be more to it, right? I haven't used the 2000 yet. Can you see how you might use WX and 2000? Well, the perimeter of the rectangle is going to be 2000. And so adding up all the sides of fencing, W plus X plus X, that's 2000. 2W plus 2X is 2000. Let's divide both sides by 2. W plus X equals 1000. Let's solve for W. W equals 1000 minus X. And now, look at this. This is why this is kind of nice, because that W can be replaced right in my equation for area. And so I get area is WX, or which is 1000 minus X times X. Let's distribute the X. And we get area is 1000X minus X squared. Hey, look at that. Once again, we have a downward opening parabola. X there. And it appears as though if X was 0, so you can imagine putting 0 in for the area function. If X is 0, then the area is 0. Right, can you imagine it would be like a very flat rectangle. Then as X increases, I get a very skinny rectangle with a little bit of area, and X gets larger and larger, then there's some maximum area, but X can't be too big, because if X is really big, then my width will be skinny, because I only have 2,000 feet of fencing. That's a constant. So there's some X value that should give me the best possible area, some X value that will maximize my area. So how do we find that X value? What maximizes area? And again, we look to a vertex. The X value of that vertex is negative B over 2A. Let's identify the B and the A. So I have 1000 is B, negative 1 is my A. And when I compute negative B over 2A, I get 500. So X is 500. If I make X 500, that will give me the largest possible area. Well, what is W then? Well, remember, W was 1000 minus x. So 1000 minus 500 is 500. So in fact, this ends up being a square, a 500 by 500 square. That is the square with, that is the rectangle that has maximum area. And the dimensions that I sought in this problem were 500 and 500. And then for what it's worth, the actual area of the rectangle now can be computed. 500 times 500 is 250,000. A suspension bridge. Suppose a suspension bridge, as pictured here, has two towers 4,200 feet apart, and each tower is 526 feet high. The hanging cable makes the shape of a parabola, and it touches the bridge between the two towers. Now, a little aside here, in real life, the cable doesn't really make the shape of a parabola, but it is pretty close, so we can run with it. Here's the question. Find the height of the cable above the road 1,000 feet from the center. So that's what's being indicated here in the diagram. I start at the center of the bridge where the cable touches the road, and I walk 1,000 feet away, and I look up above me. How high is the cable there? We'll do this. We'll solve this problem in two steps. Imagine the vertex of the parabola is at the origin. Then what is the equation of the parabola? And then once I have the equation for the parabola, we'll use the equation to solve the question. So, step 1. Imagine the vertex of the parabola is at the origin, 0, 0. What is the equation of the parabola? Well, what does a quadratic function look like in general, or the equation for a parabola? Well, I can say that f of x equals ax squared for some a. Do you remember, this is actually the vertex form of the parabola. So vertex form said that my quadratic function, f of x, has the form a x minus h squared plus k, where the vertex is at coordinates hk. Well, of course, in this case, my origin, my vertex is 0, 0, and so this just collapses into a times x squared. Okay, so I know the general form of the parabola, ax squared. What else do I know? I know the height of the bridge. I know that f of 2100 is 526. That's the height of the tower, which is 2,100 feet away from the center. So how can I use that? Oh, well, let's plug 2100 in for x in my formula. So we get a times 2100 squared is 526. And we can solve for a. A is 526 divided by 2100 squared. And that gives us the formula for our parabola. Now let's use that formula to figure out some more information. How high is the cable 1,000 feet from the center? Well, I have my formula here. All I need to do is plug in 1,000 in for x. So f of 1,000 is 526 over 2,100 squared times 1,000 squared, and it turns out that that answer is 119.3, and that's feet. So when you are 1,000 feet from the center of the bridge and you look up, that cable above you is 119.3 feet high. All right, I kind of like these three problems that show somewhat real-life circumstances in which quadratic functions play a role. And it's interesting to see how we can use those quadratic functions to analyze the situation and pull out some good information. This is a good place to stop, and this concludes Unit 6 on quadratic functions.